So in problem 24, we've got A that's similar to B, and we want to show that determinant of A is equal to the determinant of B. So we have to use what we know about similar matrices. So since A is similar to B, we got to write down what that means. Always take your given and think about what that means. Here's our given. A is similar to B, and it's the only thing that we're given. So we can say since A is similar to B, what that means is that there's an invertible matrix such that P such that A is equal to P times B times P inverse. Since A is similar to B, there is an invertible matrix P such that A is equal to P times B times P inverse. That's what similar means. That's what we're talking about with similar matrices. Now we want to show that the determinant of A is equal to the determinant of B. So what we can do is take the determinant of A and by properties of determinants, we can take the determinant of A is equal to the determinant of P times B times P inverse. And by properties of determinants, the determinant of P times B times P inverse is the determinant of P times the determinant of B times the determinant of P inverse. This is just by properties of determinants. It's this equal sign that's by properties of determinants. Now, I can't rewrite the matrix multiplication PBP inverse in a different order because matrix multiplication is not commutative. But determinants are just scalars. So multiplying determinants, that's just regular scalar multiplication. That is commutative. So the determinant of P times the determinant of B times the determinant of P inverse is equal to the determinant of B times the determinant of P times the determinant of P inverse. We can do this because determinants are scalars, and scalar multiplication is commutative. We wouldn't have to justify this, because anybody that's even capable of reading this proof is going to know that determinants are scalars. But let's be clear, since determinants are scalars, and scalar multiplication is commutative. Make sure that we are getting all of our ducks in a row, or our determinants in this case. Then once again, by properties of the determinants, the determinant of P times the determinant of P inverse is just equal to the determinant of P times P inverse. So this is equal to, I shouldn't do that. The determinant of P times the determinant of P inverse is equal to the determinant of P times P inverse. Once again, by the same properties of the determinants we had before. So this equality we get and we know that that P times P inverse, because of what invertible matrices are, P times P inverse is just the determinant, is just the identity. P times P inverse is just the identity. just what by definition of inverses. And the determinant of the identity is equal to 1 by properties of determinants. So this is by properties of determinants. And the determinant of the identity is equal to 1, just by calculation. So the determinant of A is equal to the determinant of B times, since we can rearrange the determinant of P times the determinant of B times the determinant of P inverse into the determinant of B times the determinant of P times the determinant of P inverse, we can conclude that the determinant of A is equal to the determinant of B, because all this is equal to 1. Because the P times the P inverse is all equal to 1. Any questions? So the way that this particular proof works, we're given that A is similar to B, so we have to write down what that means. Then the question is about determinants, so we should take the determinant of everything. And then once we're in the land of determinants, everything is scalar multiplication. I can't rearrange the order of P times B times P inverse because those are matrices. Matrix multiplication is not commutative. But once we are allowed to break this into scalar multiplication, that is commutative. So I can move the determinant of P over here, and it cancels out with the determinant of P inverse. Yeah, there's a lot of determinant stuff. So also in this problem is the fact that it invokes determinants, and so you're like, uh-oh, I'm going to need to know some stuff about determinants. And so you go back to the invertible matrix theorem and you start looking at properties of determinants. You might, in this case, you should write down the red and the green because we're trying to justify everything. So you're trying to make a clear justification. Otherwise, it's just a line of stuff, and it's just this long equal sign. So it gets the point across to be just writing, say, the determinant of A is equal to the determinant of P, B, P inverse, which is the determinant of P times the determinant of B times the determinant of P inverse, which is equal to, we can arrange it in a couple of different ways, but you'd say determinant of B times the determinant of P times the determinant of P inverse, which is equal to the determinant of B times the determinant of P times P, and I could have skipped one step there, oh well, which is determinant of B times the determinant of I, which is equal to determinant of B. Those are all the steps, but how do you get through all those steps? If you're just trying to make your point, the problem says show that, so you know that this is true. It's like, oh, if this wasn't true, you wouldn't be asking me to prove it. And these are the steps, and that's useful, but how do you justify every one of those steps? Because we could have also deviated from this particular plan by saying that this is equal to the determinant of B times the determinant of P, and notice that the determinant of P inverse is the determinant of P inverse. And then that is equal to the determinant of B. So we never even had to bring up the identity matrix. Determinant is a scalar. The determinant of a matrix is a scalar. And now we've got the other thing that we need from the determinant chapter. One of the things that we didn't get in the determinant chapter was that the determinant of a matrix is the product of its eigenvalues. Correct. So we can commute the, we can use the commutative property because the determinant, since it's scalar multiplication is commutative, where matrix multiplication is not. So the QR algorithm in where we're talking about before problem 23 is a factorization algorithm for factoring a matrix. One of the things that you get into in a more when you look at more linear algebra is looking at how to factor matrices. So there are a lot of important factorizations of matrices. One of them is diagonalization. That's a factorization of a matrix that has some very specific requirements. We need to have the correct number of linearly independent eigenvectors for that. There's also the CR factorization, the QR factorization, the LU factorization. There's lots of different ways to factor matrices that will help us solve matrix equations quickly. Let's take a look at the process of problem 23 though, because we're just trying to learn how things work. So let's look at 23. 23 doesn't utilize any determinants, I don't think. Let's take a look. So in 23, we have that A is equal to Q times R, and Q is invertible. If A is equal to QR with Q invertible, then A is similar to A1, which is RQ. So A is equal to QR, and Q is invertible. So I can write Q inverse, and but I can't write R inverse, and I can't write A inverse. I can only write Q inverse. That's the only thing that we're allowed to invert. All right, and we want to show that A is similar to A1, which is RQ. That means we want to show that there's an invertible matrix P such that A is equal to P times A1 times P inverse. So this is not going to be the start of our proof. This is just going to be us thinking about things. Want to find, here's our given. There's not much to work with there. I can multiply both sides by Q so that Q inverse times A is equal to R. But we want to show that A is similar to A1, which is equal to RQ. So we want to show, we want to find an invertible matrix P such that A is similar to A1. So A is equal to P times A1 times P inverse. That's what we want to show. If A is to be similar to A1, then we have to find an invertible matrix so that A is equal to P times A1 times P inverse. Let's see if we could figure out what this matrix P is. So let's do some more work here. Let's see. What can we replace? A1 is RQ, and Q is invertible, and A is QR. Oh, question? So I'm just taking what I want to find. I said A is similar to A1. We're just trying to show this part. A is similar to A1. So I'm just writing down what that means. A is similar to A1 means there's an invertible matrix P such that A is equal to P times A1 times P inverse. Just like when we looked at problem 24. Just like when we looked at problem 24, we were given that A is similar to B. Since A is similar to B, that means there is an invertible matrix P such that A is equal to PB inverse. We don't know how P ties in with RQ yet. We're just thinking about things. We're trying to figure out where's this invertible matrix going to come from. That's what we're trying to figure out. So we're looking for this invertible matrix P. Let's figure out how this ties in with RQ or QR. So A is equal to QR. We're given that A is equal to QR, and A1 is equal to RQ. So how can I turn QR into RQ? So this is equal to P times RQ times P inverse. We're just thinking about things. We're just taking the stuff that we're given and throwing it in there. How is QR is equal to RQ? What's an invertible matrix that I could put at the end of here and get the Q on the other side? So based on this information, what must Q, or what must this matrix P be equal to? What can I multiply here, where the inverse matrix, where the inverse here on the, what's that, the right side shows up on the left. And now we see what this will tell us exactly what the matrix P needs to be. What is the matrix P? So what we see is that if I put a matrix Q inverse to cancel out the Q on the left, and then I put the Q over here on the right, we can see that the matrix P that we're interested in is the matrix Q. So if A is equal to QR, where Q is invertible, then A is similar to RQ. The matrix that gives us the similarity is the matrix Q. Any questions? So A is equal to QR, and QR is, we can multiply by Q times Q inverse. So since A is equal to QR, I can multiply by the identity matrix. I can always multiply by the identity matrix. And in this case, I want to write the identity matrix as Q, I'll say R, and then the identity is going to be written as Q times Q inverse. And so this is equal to Q times RQ times Q inverse. Therefore, A is similar to RQ. A and A1 are not the same. A is QR and A1 is RQ. They're similar, but they're not the same. Matrix multiplication is not commutative. QR is not equal to RQ. But if Q is invertible, then QR is similar to RQ. Any questions? How's everybody okay? So we did find some correct. The reason that I wrote down P is because P is just, I don't know what this matrix is going to look like, but there must be some matrix out there that's invertible such that A is equal to P times A1 times P inverse. Once I filled in A as QR and wrote A1 as RQ, I was able to see that the matrix P is just the matrix Q. It was Q all along. That's Star Trek: The Next Generation solution. It was Q all along. He was just messing with us. Or space-time continuum problem. That's kind of pretty much all of Star Trek: The Next Generation. Any questions? Comments? Snide remarks? I don't know if you all know this about me, but I can actually travel in time. And I got to tell you, when I go back in time and change things, everything changes in the present time. But I'm the only person that can see that. So I'm the only person that sees all the changes, and no one, everything else just happens normally. See, watch this. I'll be right back. Whoa, everything is all different. I just went back and changed some stuff. Man, I guess the new version of me did choose this color. So I'm just using whatever identity works. So A, Q, and R must all be n by n matrices. So that's just the n size identity. Because I can always multiply by the identity matrix. And the identity matrix will always be a matrix multiplied by its inverse. Any other questions from 5.2 since we're all in 5.2 right now? All right, I'm going to pause the video and we'll see if there are other questions that we have.